पहले तो आपको काफी फायदा हुआ होगा, क्योंकि हमने पार्ट 1 में और पार्ट 2 में हमारा अप्रोच यही रहा कि दो एरियाज में जनरली स्टूडेंट्स।
Sir, we are live. We can start.
वो आपको वापस दिखाना।
Hello students, welcome to the GATE Score Booster session of Digital Circuit subject. Good morning everyone. In the last class, that means yesterday, we have discussed the questions related to the first three chapters of Digital Circuit subject, right? Number systems and codes, Boolean algebra and K-maps, and logic gates. So in this particular session, we are going to discuss the questions related to the remaining concepts, remaining chapters, right? So those are, just one second. Yeah, those are combination circuits, sequential circuits, data converters, logic family, microprocessor, etc. Right? Any students who are attending very first time regarding this GATE Score Booster session? Any new students are there? All of you please respond. Any new students are there? Or please respond. How many of you attended yesterday's class regarding digital? Okay, fine. So in this session, let us continue further questions related to the digital circuits concept, right? So all of you please respond in this. First read the question and tell me what are the concepts involved in this particular question. Yeah, very good. Tarun, Sushma, Srinivas. Yeah. All of you please read the question and tell me what are the concepts involved in this particular question. Yes, it is the question related to combination circuits, right? So here decoder is there and mux is there, right? And if you observe the fourth option, that is regarding logic gates. Okay. So first read the question. Let f of ABCD equal to B bar D plus BD bar plus AC bar. Choose the correct option or options regarding the Boolean function f of ABCD. F of ABCD. So option A is what? The minimum number of 2/1 muxes required for implementing f of ABCD is 4. Option B, we can implement f of ABCD by using a 4 to 16 decoder and a 10 input OR gate. Option C is we can implement f of ABCD by using 4 to 16 decoder and 6 input NOR gate. 6 input NOR gate. Option D, minimum number of 2 input NAND gates required. Minimum number of 2 input NAND gates required is 5 if both normal and complementary inputs are available. Okay. So here he has given one expression. We have to check whether whatever the choices they have mentioned, whether those are correct or not. Whichever correct options are there, we have to choose all the correct options, right? Yeah, first note down the given function. All of you note down the given function. F of ABCD. F of ABCD is equal to B bar D plus BD bar plus AC bar. A into C bar. This is the given expression. B bar D plus BD bar plus AC bar. Here the question is what? Option A is corresponding to 2/1 mux. For 2/1 mux, what is the standard equation? Output of 2/1 mux. What is the standard equation for 2/1 mux? Y equal to, for 2/1 mux, how many selection lines you will be having? How many selection lines you will be having for 2/1 mux? One selection line, right? Yes. Because you're having two inputs, you can choose one among those two inputs with the help of one selection line, right? Yes. So the standard equation is S bar I naught plus S into I1. That means if selection line is 0, I naught will be converted to the output. If selection line is 1, I1 will be converted to the output, right? That is the functionality of 2 by 1 mux. At any time, only a particular input will be converted to the output, right? So this is the standard equation regarding 2 by 1 mux. Now, here, whatever the expression is there, this one, if you observe, just a second, up to this one, what is this expression? B bar D plus BD bar. It is nothing but which function? This is XOR, right? Yes, it is XOR function, right? Very good. So now use this standard equation. Use this standard equation in order to get B exclusive or D. B exclusive or D. So directly write here B bar D plus B into D bar. So that means here the selection line is B, selection line is B, I naught is D, I1 is D bar. Here selection line is B, I naught is D, I1 is D bar. I1 is D bar. Okay. B bar into D plus B into D bar. Selection line is B, I naught is D, I1 is D bar. So how you can implement D bar? Here the question is, we have to implement this particular function by using 2 by 1 muxes only. Only 2 by 1 muxes are allowed, right? So now we have to implement D bar. We have to implement D bar. So how we can implement? Use the same standard equation. Use the same standard equation. D bar into I naught is 1 plus D into I1 value will be 0. So in this case, I have chosen D as a selection line. D as a selection line. If you make I naught value 1, I1 value 0, then you'll get D bar, D bar, right? So here selection line is D. I naught equal to 1, I1 equal to 0, I1 equal to 0. Okay. So for implementing B exclusive or D, how many 2 by 1 muxes we required? Up to this step, tell me the answer. We'll proceed further. For implementing B XOR D, how many 2 by 1 muxes we require? Yes, we require two 2 by 1 muxes. Two 2 by 1 muxes. See, the answer will vary based on the context. The answer will vary based on the context. In the question, he didn't mention regarding complement inputs, right? So whenever you require complement inputs, okay, if they don't specify in the question, in order to generate the complement inputs, either you require NOT gate or you have to implement with the help of one more mux. Okay. So here I have implemented D bar with the help of one more mux. Okay. With the help of one mux, selection is B, I naught is D, I1 is D bar. But D bar we have to generate with the help of one more mux. So that means we require two 2 by 1 muxes. Okay. But sometime in the question they will specify the complement inputs are also available. In that case, what is the answer for implementing BXRD? For implementing BXRD, if the complement inputs are available, if they specify in the question, then how many 2 by 1 muxes we require? Yes, we require only one, right? Yes, very good. We require only one. And in the question, if they specify, you are allowed to use inverter also. Then also, if only the normal inputs are available, if the inverter is allowed to use, then also you require only one 2 by 1 mux, like that. So based on the context, the answer will vary. So you have to be very careful while you're answering the questions related to minimum number of logic gates or minimum number of muxes, etc. Please read the question carefully, whether the complement inputs are available or not, whether the inverters are allowed or not, like that. Okay. If they are allowed, then based on the context, the answer will vary. Okay. Right. So up to this particular expression, we got two 2 by 1 muxes we require. Now just observe this expression, A into C bar, A into C bar, A into C bar. So this one I will write as C bar into A, C bar into A. Okay. So that means in this standard equation, I will write like this, C bar into A plus C into 0, 0. So that means here selection line is C, I naught is A, I1 is 0. I'm repeating once again. Selection is C, I0 is A, I1 is 0, right? So here you're getting normal input only, normal form only, right? So that's why for implementing AC bar, you require only 1 2 by 1 mux. You require only, for implementing AC bar, you require 1 2 by 1 mux. 1 2 by 1 mux. Okay. So what we have done, whatever the given expression is there, we have made into two parts. One part is exclusive OR function, another function is logical AND, but one variable is complement version, right? Now, if you observe the overall function, just assume this, just one second. If you assume this is like x1, this is like x1, and this is like x2. This entire combination is x1, this particular term is x2. It is something like x1 plus x2. X1 plus x2, that means what? Logical OR. That means you have to implement logical OR function, right? So just write the truth table regarding x1, x2, regarding logical OR operation. 0 0 0 1 1 0 1 1. You are very much familiar regarding logical OR among the two inputs. Write the output 0 1 1 0 1 1. Now for the time being, if you choose x1 as selection line, then just observe here. Here selection value is 0. Here selection value is 1. Okay. Now with respect to 2 by 1 mux, if the selection is 0, then I0 will be converted to the output. If the selection is 1, I1 will be converted to the output, right? So just observe here, whatever the x2 value is there, that you are getting at the output. So that means I0 value is nothing but x2. Now tell me, what is I1 value? All of you please respond. What is I1 value? I1 value is 1. Very good. Very good, Srinivas. 1. See, just observe. You have to observe the output with respect to another variable. Whether the x2 is 0 or x2 is 1, you are getting output as 1. Right? Whereas here, what are the x2 value is there that you are getting at the output? Okay. Right. Yes, very good, Michael, Priya. Yes, I1 value is 1. So that means the f of ABCD function, just one second. F of ABCD function I'm writing like this: B exclusive RD, B bar D plus BD bar. I'm writing as B XRD plus another term is A into C bar. This is your x1, this is your x2 for the timing, for easy understanding. Okay. So you're having 1 2 by 1 mux. So you're having 2 by 1 mux. Here inputs are I0, I1. And you're having one selection line S. Output is f of ABCD. So here, for the timing, I have considered x1 is selection line, that is nothing but B exclusive RD. Okay. Here I0 value is x2. X2 is nothing but A into C bar. And I1 value is 1. So that means if you observe here, for implementing BXRD, you require 2 2 by 1 muxes. For implementing AC bar, you require 1 2 by 1 mux. Okay. For implementing this logical OR operation, right, you require one more 2 by 1 mux. So just add all those three, you'll get 2 plus 1 plus 1. That means you require 4 2 by 1 muxes. For implementing the given function. We require 4 2 by 1 muxes. So whether option A is correct or not? Option A. The minimum number of 2 by 1 muxes required for implementing f of ABCD is 4. So that means it is correct one. Option A is correct. Right. So now we have to verify the remaining choice also, whether those are correct or not, one by one. Okay. So option B, option C, if you observe, here the function implementation by using decoder and some other gate. Okay. So how we can implement any particular function by using decoder? What is the condition? The given function should be in which form, so that you can easily implement with the help of decoder and some other logic gates. Or otherwise, I will ask in other way, how we can get minterms from the decoder. How we can get the minterms from the decoder. What is the condition regarding enable? In general sense, if you are considering normal enable, what should be the value of enable in order to get the minterms from the decoder? Yes, enable equal to 1, right? When enable equal to 1, the outputs of the decoder are nothing but minterms, right? Minterms. So once if you got the minterms from the outputs of the decoder, based upon your function, sum of minterms, whichever minterms are there, which you are supposed to add in your logic function, so you can pass through OR gate, right? So like that. So if you observe the given function, that is SOP, so you have to convert into sigma m format. Sigma m format. So write once again the given function. Now we are verifying regarding option B. Option B. The given function, note down once again, f of ABCD equal to B bar D plus BD bar. B bar D plus BD bar plus A into C bar. A into C bar. So this particular function is SOP form. SOP form. In order to convert into sigma m, we know the shortcut method, right? So all of you try to follow the shortcut method. First write the variables order as it is, ABCD. Then consider term by term, B bar D. That means B value is 0, C value 1. Sorry, D value 1. B value 0, D value 1. Here AC values are unknown. AC values are unknown. So you'll get 4 combinations. You'll get 4 combinations. So here I am not writing what are those minterms. Okay. Just in order to make it simpler, I am not writing what are the minterms. Okay. Just if you observe the question, what he has mentioned, option B, we have to verify. We can implement this particular function by using a 4 to 16 decoder and a 10 input OR gate. That means OR gate inputs are 10. And another case is what? By using 4 to 16 decoder and 6 input NOR gate. So we have to check how many inputs we have to connect. We have to give to the respective logic gate. That one only our requirement. Not what are the exact minterms. Okay. So that's why I will follow different method. Okay. Since we have discussed what are the minterms in the last class, so that method I am not discussing. Directly I will count how many minterms you will get. So this one I am labeling as number of P. So since 2 bits are unknown, you will get 4 combinations. That means you will get 4 minterms. Next one is what? B into D bar. B value 1, D value 0. How many minterms you will get in this case? How many minterms you will get? Regarding BD bar, total how many minterms you will get? 4, right? Yes. Similar to this one. Yeah. 4. Next, consider A into C bar. A into C bar. That means A value is 1, C value is 0. Here also you will get 4. Here also you will get 4. Okay, when you consider only this term, you are getting 4. Similarly here 4. Similarly here 4. Okay. Now you have to consider 2 terms at a time. That means you have to multiply. Simple. B bar D into BD bar, you will get 0. So here number of P intersection Q, that is 0. See, B into B bar is 0. Okay. Now multiply these two. Sorry. Multiply these two. How many minterms you will get? You will get A, B, C bar, D bar. That means you are getting how many minterms? Just multiply these two. How many minterms you will get? Only one, right? See, when you multiply these two, you are getting what? One product term A, B, C bar, D bar. A, B, C bar, D bar. That means you are having all the 4 literals, right? Yes, only one minterm you will get. Similarly, multiply these two. Multiply these two. N into N of P intersection R. N of P intersection R. How many minterms you will get when you multiply these two? Here also you will get 1 because A, B bar, C bar, D, right? Now combine all the 3. That means you have to multiply all those. Multiply all these terms. Then obviously the resultant value is 0, right? I hope you learned this particular formula in your math mathematics in the school standard, right? 10th class or 8th to 10th. Okay. So number of in sets and unions, you might have learned, right? Number of P union, Q union, R is equal to number of P plus number of Q plus number of R minus number of P intersection Q minus number of Q intersection R minus number of P intersection R plus number of P intersection Q intersection R. Right? Whether all of you familiar about this formula or not? I hope all of you are familiar. Please respond whether you are familiar about this formula or not. Right? Yes. Very good. Okay, just add all these three, you will get 12. So this combination you are getting 12. If you take minus common, then here just add these two, you will get 2. Minus 2, this term is 0. So 12 minus 2 is 10. So that means here what happened? In these 12 terms, two terms are repeated, right? Two terms are repeated. So different minterms are 10. Total number of unique minterms present in this particular function are 10. Present in this particular function are 10 minterms. Okay, the number of minterms are 10. Suppose, just for easy understanding, I am considering, just for example, if you are having one function like this, m1 plus m2 plus m3. Okay, you are having one function which consists of 3 minterms. Okay, m1 plus m2 plus m3. Now, with the help of one decoder, you will get the minterms. For the timing, I am considering 2 to 4 decoder. Okay, here enable value is 1. Here the inputs are AB. So when you keep enable equal to 1, the outputs are nothing but minterms, m0, m1, m2, m3. You will get 4 minterms, right? m0, m1, m2, m3. Now, since you are having m1 plus m2 plus m3, you require OR gate. So you will pass the respective minterms as inputs for this particular OR gate, right? Yes or no? So that means if you are having the output function as sigma m format, so with the help of decoder, when you keep enable equal to 1, outputs of the decoder are nothing but minterms. Whichever minterms you have to add or sum together, those minterms you will pass through logical OR gate, right? So here if you observe, the given function f of ABCD consists of 10 minterms summed together, right? It is sigma m format. You're having 10 minterms. Okay, what are those minterms? For the timing, I'm not representing, just to save the time. Okay, I'm not representing, but in that particular function, you're having 10 minterms. Okay, so that means if you keep enable value 1, outputs of the decoder are nothing but minterms. After that, you will pass the respective 10 minterms through a 10 input OR gate, right? So here, if you observe, the given function, it is a function of 4 variables. So now, what is the size of the decoder we have to consider? What is the minimum size of the decoder we have to consider? In order to produce, since you're having 4 variables, you will get 16 minterms. Since you're having 4 variables, you will get 16 minterms. So what is the size of the decoder? Yes, 4 to 16 decoder. Yes, very good, Michael. We require 4 to 16 decoder. Since you're having 4 inputs. Okay. So when you keep enable equal to 1, that time you'll get outputs as minterms. Okay. So whatever the respective minterms are there in this particular function, we will pass through a 10 input OR gate. So that means option B is correct, right? Just observe option B. We can implement f of ABCD by using a 4 to 16 decoder and 10 input OR gate, right? Option B is correct. Now let us verify regarding option C. Regarding option C, see, for the timing, just for easy understanding, let us consider the same example. Okay, m1 plus m2 plus m3 is there. The same function. How we can write? Can I write capital M0? The same function. we can, since you're having 4 combinations, since you're having 2 inputs, you'll get 4 combinations, right? But among those 4 combinations, 3 are the minterms. Obviously, the other will be the maxterm, right? But if you're having in this particular function only 2 minterms, then other 2 will be the maxterm. But in this case, I have considered 3 minterms, so only one maxterm is there. Only one maxterm is there. Okay. But okay, if you consider some other example, for the timing, if you consider this one is m0 plus m1, then in that case it will be m2 plus m3, sorry, m2 into m3. I'm considering one more example. If you are considering the function as m0 plus m1, then the corresponding function you can write in other way as m2 into m3, right? This is what? Product of max terms. Can we write like this or not? All of you please respond. Yes or no? Please respond. If you are having the function like this, m0 plus m1, the same function you can write as m2 into m3. m2 into m3, right? We can write. Because we can write any particular function, either sigma m format or pi capital M, right? So this particular function m2 into m3 is there. Apply 2 times complement, you'll get the same functionality. So apply De Morgan's law for inner complement. So that means m2 bar plus m3 bar whole bar, right? So capital M2 bar, capital M3 bar, how we can write? These are the complement of max term. What we can write? Complement of max term is nothing but, all of you please respond. Complement of max term is nothing but min term, right? Yes, very good. Michael, Srinivas. Yeah, it is the min term. That is M2 plus M3 whole bar. Now just observe. Previously, you're having M1 plus M2 plus M3. Just I have considered one normal example, right? So outputs of the decoder are nothing but min terms. Those min terms you can pass through OR gate. But here, if you observe M2 plus M3, you're having another example I have considered. But on top of it, you're having complement. That means this particular function you can implement by using which gate? NOR gate, right? Yes, very good. Rashtrikar, yeah, very good. NOR gate. By using NOR gate, we can implement. That means whenever you're having decoder and NOR gate, right? So that means whenever the requirement is implementation by using NOR gate, then you should consider the function as product of max terms, right? After that, you have to apply 2 times complement. For inner complement, use De Morgan's law. After that, you will get sum of min terms under the complement, right? So you have to pass the respective min terms through the NOR gate, okay? So if you observe, previously we got for 4 variables, total combinations, you will get 16 in terms of zeros and ones, right? Out of which 10 combinations are the min terms. That means how many max terms you will get? Number of max terms in the same function. Number of max terms in f of ABCD. How many you will be having? Yes, you will be having 6, right? Total combinations are 16, out of which 10 combinations are min terms, right? Remaining 6 combinations will be max terms, right? Okay. So that means here you will be having pi capital M. I'm not specifying what are those max terms, but here you will be having 6 max terms. Okay. So you will follow the same approach. So that means here you require NOR gate. Okay. 6 input NOR gate you require. And the same thing, 4 to 16 decoder you require. 4 to 16 decoder, you will keep enable equal to 1, outputs will be min terms. And in this case, whatever the respective min terms you will get, so those min terms you will pass through NOR gate. Okay. So here NOR gate, the number of inputs for a NOR gate required is 6. So that means option C is also correct, right? We can implement f of ABCD by using 4 to 16 decoder and 6 input NOR gate. Is it clear up to option C? If you're having any doubt, you can ask. Is it clear, all of you? Yeah. So in this way, what sometimes they will give one decoder, and after that they will give some logic gate. Okay, they will connect the outputs of the decoder to the logic gate, and they will ask the output function either simplified form or sigma format or pi capital M, etc. Okay. So here we have discussed another variety regarding that particular case. Okay. And the option D. All of you try option D. Since we have discussed the questions related to logic gates, so all of you try to solve, and how many two input NAND gates we require for implementing the given function. Here he has mentioned if both normal and complement inputs are available. Both normal and complement inputs are available. I will give time. All of you please try to solve and tell me whether option D is correct or not. Because this question is related to logic gates, right? We already covered in the last class. What is the answer you are getting? Whether option D is correct or not, or how many two input NAND gates you are getting for implementing this particular function. Yes, Srinivas is getting 4. Okay, we'll see. Okay, all of you please try. And cross check. Okay, all of you pay attention here. We will apply 2 times complement. Yes, Priya is getting 5. Yeah. So here this particular function is SOP form. SOP form. Whenever you are having SOP form, it is easy for us to implement by using NAND gates, right? So you have to apply 2 times complement. For inner complement, apply De Morgan's law. Apply De Morgan's law. That means BXRD complement. First term complement and second term complement. And you're having actual complement as it is. Now, this one you can write as BXRD complement. That is nothing but BX NOR D. You can write complement of XOR is nothing but XNOR. Then you're having actual complement as it is. Now write this particular expression BX NOR D. How many two input NAND gates we require? Let us verify. How many two input NAND gates we require? Let us verify. BX NOR D is nothing but B bar D bar plus BD. This particular function is SOP form. Yes or no? Similar to here, SOP form. In order to implement by using NAND gates, you have to perform 2 times complement. Okay. For inner complement, apply De Morgan's law. That means first term complement and second term complement. And you're having external complement as it is. Now tell me, for implementing 2 input XNOR gate, how many 2 input NAND gates we require? How many 2 input NAND gates we require? Just observe this particular expression. How many 2 input NAND gates we require? 3, right? Yes, very good. Here B bar D bar is available because in the question they mentioned complement inputs are available, right? You don't need to implement separately by using another logic gate. So here you require 1 gate, here second gate. Consider this is like X1, this is like X2. So X1, X2 whole bar, that means 1 more gate. So that means you require 3 2 input NAND gates. We require 3 2 input NAND gates. We require 3 2 input NAND gates. Okay. For implementing BX NOR D. For implementing BX NOR D, you require 3 2 input NAND gates. Now, for implementing a C bar whole bar, we require 1 because C bar is already available, right? Consider this like x1, this is like x2. x1, x2 whole bar means 1 more. That means 3 plus 2. There's nothing but 5. Yes or no? We require 5 2 input NAND gates. We require 5 2 input NAND gates. Is it clear? So that means option D is the correct one. Option D is the correct one. Here we require 5 2 input NAND gates if both normal and complement inputs are available. So for this question, all the 4 choices are correct. All the 4 choices are correct. Is it clear? Any doubt is there regarding the number of NAND gates? 5. I hope it is clear, right? Yeah. Next question. The functionality implemented by the circuit below is. Here he has given one buffer. Input is there, output is there. Whatever the input is there, that will be connected to the output when enable equal to 1. It is a tri-state buffer. Okay. When enable equal to 1, that time only input will be connected to the output. Otherwise, it will go into high impedance. High impedance. That means input won't be connected to the output. Okay. And here he has given one circuit diagram like this. And he has given 4 choices like this. So we have to figure out which is the correct option. Either 4 by 1 mux, 2 by 1 mux, 7 by 1 or 8 by 1. Yeah. All of you just observe here. Here you are having XOR gate, here XNOR gate is there. XOR gate, XNOR gate, inputs are same, AB only. Okay. So XOR gate, XNOR gate, functionality is what? Complement each other, right? If this is producing 0, this will produce 1, or if this is producing 1, this will produce 0. Yes or no? Either 0 1 case or 1 0 case you will get. Here you are having simply OR gate, simply OR gate. So I value is what? All of you please respond. What is I value? I value is 1, right? 0 plus 1 or 1 plus 0. You will get 1. 1. Okay. Now, this is the demux. Demux. The functionality is controlled, decided by the selection lines, right? Whatever the input is there, this particular input will be connected to one of the 2 power n outputs based on the selection values. Based on the selection values. Now, just observe. Here you are having NOR gate. NOR gate. One input is 1. One input is 1. Whatever may be the other value. Whatever may be the other value. What you will get here output? This is NOR gate. NOR gate. One input is 1. Whatever may be the other value. Irrespective of that, what is the output you will get here? Zero, right? Yes, very good. Very good, Srinivas. Yeah, 0. Because here you're having NOR gate. 1 plus anything is 1. Complement of 1 is 0. Complement of 1 is 0. Here you're having NAND based inverter. That means output you will get complement of input. 0 bar is 1. 0 bar is 1. Here you're having exclusive OR gate. Exclusive OR gate. 1 XOR 1 is 0. So that means you got S1 equal to 0. So just 1 second. I will write here. I value is 1. I value is 1. Selection line S1 is 0. S1 is 0. Now let us determine S0 value. S0 value. Here you are having exclusive OR gate. Okay, inputs are C and 1. Okay, so that means here I will write C bar into 1 bar plus C into 1. That means you will get C. So S0 is nothing but C. S0 is nothing but C. Right. So just 1 second. So C value can be 0 or C value can be 1. C value can be 0 or C value can be 1. Now, I value is 1 only. Selection line value S1 is 0. Here also selection line is 0. Okay. Now just observe. Here input is 1. Input is 1. Selection line values S1, S0. That is 0, 0. 0, 0 case. 0, 0 case. The input will be connected to y0. Input will be connected to y0, right? Y0. So that means y0 is getting, in this case, just 1 second. In this case, y0 is getting 1. Y0 is getting 1. So that means this particular buffer is enabled. This particular buffer is enabled. Whatever the input is there, that particular input will come to the output, right? So that means here y equal to w. Okay. Next. In this case, selection value is 0, 1. For 0, 1 case, y1 will be 1. Now tell me what is the output you will get? What is the output you will get? Output y will be connected to which input? X, right? Yes, very good. Because in this case, this particular buffer is getting enable value is 1. So here the input is X, that will come to the output. Okay. So that means overall, if you observe, you're getting the output either W or X. Yes or no? You're getting the output either W or X. Okay. And since you're having 4 choices or multiplexer, right? Either you're getting W at the output or X at the output based on the C value. Because here S value is 0, S1 value is 0, right? So that means which option is the correct? Which option is the correct among the 4 choices? It is very simple. Yes, option B, right? 2 by 1 marks. You're having 2 inputs, WX. At any time, only one particular input will be connected to the output, right? It is a 2 by 1 marks. 2 by 1 marks. Yes, very good, Rajshekhar, Srinivas, Priya. Yeah. Next question. The following circuit acts as. Here he has given one flip-flop, that is D flip-flop. Okay. And he has given some circuit diagram here. And he is asking, what is the overall circuit? Overall circuit. Based on the given choices, you can look at the choices and you can verify. Whichever option satisfies, that will be the correct one. So for solving these type of questions, first you have to write the characteristic equation of the given flip-flop. Characteristic equation of the given flip-flop. So what is the characteristic equation of D flip-flop? Q of t plus 1 equal to what? Characteristic equation of D flip-flop. Q of t plus 1 equal to D, right? Q of t plus 1 equal to D. This is the characteristic equation of D flip-flop. Characteristic equation of D flip-flop. Right? See, related to flip-flops, if you remember the characteristic equations, whenever they give the circuit diagrams like this, and they may ask, what is the output you are getting, or what is the overall circuit behavior, which flip-flop it represents, right? So for solving those type of questions, whatever the given flip-flop is there, first write the characteristic equation of that particular flip-flop. After that, for D flip-flop or T flip-flop, you'll be having only one input. For SR or JK, you'll be having 2 inputs, right? So you have to determine what are those inputs from the given circuit diagram and substitute and do the simplification. Okay, like that you have to proceed. So here D is nothing but output of this gate. Now just observe what is this particular circuit. Whatever the circuit diagram here you're having, this circuit diagram is nothing but which logic gate it represents, the overall circuit. Any idea? What is this combination? What is the circuit diagram here present? This one you can replace with one logic gate. What is that logic gate? XOR. Very good, Srinivas. It is XOR gate. In the 3rd chapter, logic gates, okay, regarding implementation of various gates by using NAND, by using NOR, we have discussed, right? So there, for implementing XOR gate, we require only 4 NAND gates. For implementing an XOR gate, 2 input XOR gate, we require 4 NAND gates, right? So this particular circuit diagram you can replace simply with XOR gate. XOR gate. Okay. So for this particular XOR gate, you are having 2 inputs. Here PQ you are getting PQ, and here another input is Q of t. Q of t. Okay. Q of t. Now just substitute here PQ exclusive or Q of t. PQ exclusive or Q of t. See, in the regarding 4 flip-flops, okay, you will get XOR operation in which flip-flop regarding characteristic equation among all the flip-flops. You will get in the characteristic equation exclusive OR operator. In which flip-flop you will get? In which flip-flop characteristic equation you will get XOR operator? T flip-flop, right? Yes, very good. Very good, Michael, Rajshekhar, Srinivas. Yeah. T flip-flop, right? Among the 4 choices, you're having T flip-flop in only option C. In only option C, right? So just consider if P equal to Q equal to T, if P equal to Q equal to T, that means P and Q. That is nothing but T and T. That is nothing but T, right? So T exclusive or Q of T. So Q of T plus 1 equal to T exclusive or Q. There is nothing but characteristic equation of T flip-flop, right? So it is matching. So option C is the correct one. So in this way, you have to proceed whenever you are getting the questions related to this particular model. Next question. If the initial state of the following sequence circuit is Q3, Q2, Q1, Q0 equal to 0, 1, 0, 1. Okay. Then the decimal equivalent of the state Q3, Q2, Q1, Q0 after applying 423rd clock pulse will be dash. After applying 423rd clock pulse will be dash. So here he has given one circuit diagram and he has mentioned initial state. Okay. And he is asking what is the state you will get after applying 423rd. Okay. So before finding this one, okay, first let us try to understand this particular operation. This particular given circuit, how many states it is going to repeat. From there we can find the mod value. Okay. After that we can proceed further step. Okay. So whenever you are getting the questions like this, okay, first make the tabular form. So first column is clock. Here you're having all the flip-flops are D flip-flops. So write the D flip-flop inputs. D3 is nothing but Q2. D3 is nothing but Q2. Right. Next, D2 is nothing but Q3. D2 is nothing but Q3. Next, D1 is nothing but Q0 bar. Next, D0 is nothing but Q1. See, just look at the circuit diagram and write the inputs. So since you're having 4 D flip-flops, okay, you'll be having 4 inputs, D3, D2, D1, D0. Okay, and you'll be having 4 outputs. Outputs are Q3, Q2, Q1, Q0. 4 outputs. See here Q3, Q2, Q1, Q0. These are the outputs. Initially, what he has mentioned, initial state 0, 1, 0, 1. Initial state is 0, 1, 0, 1. 0, 1, 0, 1. Now, in the absence of clock signal, right? Initial state he has mentioned like this. Okay. So with the help of this one, now you can determine the inputs here. Q2 is nothing but 1. Q3 is 0. Q0 bar, that is 1 bar is 0. Here 0. Okay. Now just observe the circuit diagram carefully. Since you are having D flip-flop, characteristic equation is Q of T plus 1 equal to D. That means whatever the input you're having, you will get at the output when you're getting the respective positive edge of the clock signal or respective negative edge of the clock signal, whichever they represent for that particular flip-flop, right? So if you observe these two flip-flops are having external clock signal same. The same common clock signal is there for these two flip-flops, right? And here it is a positive edge. That means whenever the clock signal changes from 0 to 1, that time whatever the D3 input is there, that you will get here. Whatever the D2 input, that means earlier Q3 or D2 input, that you will get here. Because for these two flip-flops, the same common clock signal. Whenever you are giving first time positive edge, second time positive edge, third time positive edge, like that. Okay. For each and every positive edge of the clock signal, whatever the input here available, it will come. Whatever the input earlier you're having, it will come here. Up to this point, is it clear, everyone? Any doubt is there? All of you please respond up to this point. Whether is it clear or not? Clear? Right. Very good. Now just observe these two flip-flops. These two flip-flops are negative edge triggered. Okay, negative edge triggered. But for these two flip-flops, clock signal is what? Clock signal is Q2. Q2. The output of this flip-flop we are giving as clock, right? So for these flip-flops, what are the input you're having? It will come here. The condition is what? Whenever you are getting Q2 value changes from 1 to 0. Q2 value changes from 1 to 0. That means it is a negative edge. Whenever Q2 signal changes from 1 to 0, that time only here, what is the input you are having? It will come as the output. That's all. So the flip-flop operation mainly affect only at the edges, either positive edge or negative edge. They will specify in the circuit diagram. Okay. Now first time I am applying external clock signal positive edge. So that time what will happen? Here 1 0 you are having, this 1 0 will come here. See, D3, D2 are the inputs, output you will get Q3, Q2. Okay. Next, just observe here, Q2 value changes from 1 to 0. Q2 value changes from 1 to 0. That means here you are getting, for these two flip-flops, you are getting the negative edge clock signal, right? Negative edge of Q2. So that means what are the input you are having, you will get here. Okay. Now with the help of this one, you determine the inputs here. Q3 value 1, Q2 is 0. Next, Q1 is 0. Q0 bar is 1. Q0 bar is 1. Now second time I am applying external clock pulse. Okay. So whatever D3, D2 you are having, you will get here. 0, 1. 0, 1. Now just observe whether Q2 is positive edge or negative edge. Q2 is changes from, just one second. Q2 is changes from 0 to 1, right? It is positive edge. So that means here output will remain same. Output will remain same. Is it clear? Any doubt is there? See, for these two flip-flops, when you get Q2 changes from 1 to 0, that time only what are the input you are having, you will get as the output. Otherwise, it will remain in the same state. Now, with the help of this one, determine the inputs here. Q3 0, Q2 1. Next, Q1 is 0, Q0 bar is 1. 0, 1, 0, 1, right? Now, third clock pulse I am applying. Now, here you will get 1, 0. Now, in this case, you are getting 1 to 0. Q2 value changes from 1 to 0. So, what is the input you are having, you will get as output. Okay, right. Similarly, continue the process. 1, 0. Here, Q1 is 1. Q0 bar is 1. 0 bar is 1, right? Fourth clock pulse. Here you will get 0, 1. Now in this case it is positive edge, right? So it will remain same. Right, once again here Q3 values, 0. Q3 0, Q2 is 1. Next, Q1 is 1. Q0 bar is 1. Fifth clock pulse. You will get 1, 0. Now just observe it is negative edge. So what are the input you are having, you will get as output. Okay. So Q3 is 1, Q2 is 0. Then Q1 is 1, Q0 bar is 0. Now sixth clock pulse, 0, 1 you will get. Now it is a positive edge, so it will remain same. Just one second. Now with the help of this one you can write Q3 is 0, Q2 is 1, Q1 is 1, Q0 bar is 0. Seventh clock pulse you will get 1, 0. Here 1 to 0 transition. So what is the output here you will get? All of you please respond. Here for these two bits, what is the output? 0, 1. Yes, very good, Michael. because here you're having 0, 1. So you'll get output as 0, 1, right? Next, Q3 is 1, Q2 is 0, Q1 is 0, Q1 is 0, Q3, Q2, Q1, right? Q0 bar, that is 0. Next, 8th clock pulse we are applying. Here you will get 0, 1. Since it is a positive edge, it will remain the same, right? Now just observe. Here you are getting initial state. Initial state you have considered 0, 1, 0, 1. Initial state you have considered 0, 1, 0, 1, right? The same state you are getting here. The same state here also you are getting, right? So whatever the initial state you're having, in order to bring the counter to the same state, how many clock pulses you're applying? 8. How many clock pulses you're applying? That is 8. Or in other words, you can say whatever the counter or sequence circuit he has given, that particular sequence circuit will repeat these states. What are the states here present? All these states it will repeat. Yes or no? Here it is starting from 0, 1, 0, 1, then 1, 0, 0, like that it will change from one state to another state for each and every external clock pulse. After reaching to the original state, if you apply further clock pulse, you will get this one, next clock pulse, this one, like that the process will continue. That means whatever the given circuit or counter, how many different states it is going to repeat. How many different states it is going to repeat. Here also if you count how many states you're having, just count how many different states you're having. 8. Yes, very good. Here we're having 8 states, right? Yes. The number of states are 8. So with respect to this or with respect to this, we can define it is a mod 8 counter. Mod 8 counter. It is very simple. Whatever the counter you're having, whatever the initial state is there, in order to bring the counter to the same state, how many clock pulses you have to apply, or the particular counter is repeating how many unique states or how many different states. With respect to that, you will get the mod number. So that means the given circuit is a mod 8 counter. Mod 8 counter, right? So here the question is, after applying 423rd clock pulse, what is the state of the counter, right? So that means if you continue like this, right, 9th clock pulse, 10th clock pulse, like that, if you do for 423rd, your entire exam time will be over for this particular question, right? So instead of like that, what you can do, just if you observe this mechanism, whatever the initial state you're having, you're getting the same state after applying 8th clock pulse. That means at 9th clock pulse, you'll get this one, 10th clock pulse, this one, like that is coming, right? So here, if you observe, the word here we have given, it is mod. Mod is nothing but modulus, right? So in the question, they have asked for 423rd clock pulse, right? So whatever the mod number is there, okay, divide the requirement. After applying 423rd clock pulses, you are supposed to know the state of the counter, right? So divide this particular number with this mod value. 8 5s are 40, remainder is 2, 3. 8 2s are 16, remainder is 7, right? So that means whatever the state you'll get after applying 423rd clock pulse, the same state you'll get after applying 7th clock pulse. Right? So that means after applying 7th clock pulse, the state is this one, 1001. Okay, so this is the binary format. Convert into decimal, you'll get 9. So answer for this question is 9. Is it clear? Any doubt? Why we have done like this operation? Because here, what is the remainder you are getting? That is nothing but modulus, right? We are considering that. Yes, very good, Rajshekhar. Michael, yeah. Is it clear why we have done like this division operation here? See, if you're having any doubt, it is very simple. What you can do, say for example, if you are supposed to know what is the state of the counter after applying 10th clock pulse, Since it is a mod 8 counter, divide this number with 8. 8 ones are 8, remainder is 2. That means whatever the state you will get after applying 10th clock pulse, the same state you will get after applying second clock pulse, right? So just observe, after applying second clock pulse, this is the state. The same state you will get after applying 10th clock pulse, because 8th clock pulse you are getting state, 9th clock pulse, 10th clock pulse, like that. So here it is a modulus operation, modular division we are performing, right? Okay. So this is the conventional approach. This is the conventional approach in order to attempt any question related to the sequence circuit. Whatever the flip-flops they have given, regarding those flip-flops, you have to determine the inputs here, and for each flip-flop, write the outputs here. Okay. Before applying the clock pulse, whatever the state is there, you have to consider. With respect to the state, you can determine the inputs before applying the next clock pulse. When you're applying the next clock pulse, positive edge or negative edge, according to that, okay, before that particular edge you're applying, what are the inputs you're having? Based on that, your output will be affected. In this case, we have considered D flip-flops. So Q of t plus 1 equal to D. Q of t plus 1 equal to D. So similarly, for JK flip-flop, you'll be having one characteristic equation, SR flip-flop, T flip-flop. So accordingly, based on the inputs, your output will be affected only at the edges, either positive edge or negative edge, based on the representation they specify in the question, circuit diagram. Okay. So the same question, if you get in your GATE exam, okay, you don't follow this entire procedure, it will be time consuming. Okay, just observe the given circuit. Just observe the given circuit. What is this particular circuit? What is this particular circuit? Just recollect your counters concepts and tell me what is the name of this particular circuit. Yes, very good, Rajshekhar. It is a ring counter. Yes, very good. Ring counter. See, in the ring counter, for all the D flip-flops, you will use D flip-flops. For all the D flip-flops, you will be having same common clock signal. Same common clock signal. Okay. Output of one stage will give as input for next stage. The last stage normal output will give as the serial input for the starting stage, right? So it is a 2-bit ring counter. It is the 2-bit ring counter. It is the 2-bit ring counter. Okay. Now if you observe this part, here you're having two flip-flops, two D flip-flops. The clock signal is same. Clock signal is same for these two flip-flops. Okay. And here in this case, Q0 bar, we are giving as serial input. What is the name of this particular circuit? What is the name of this particular circuit? Johnson counter. Yes, very good, Rajshekhar. Yeah, Johnson counter. It is a 2-bit Johnson counter. 2-bit Johnson counter. 2-bit Johnson counter. Okay. For this particular counter circuit, you're giving the output of this particular stage as the clock signal, right? So I will represent here. You're having, just one second. You're having 2-bit ring counter. First circuit I have replaced with 2-bit ring counter. Okay. Second one is what? 2-bit Johnson counter. 2-bit Johnson counter. 2-bit Johnson counter. Okay. Right. This is 2-bit ring counter. Another block is 2-bit Johnson counter. So here you're having external clock signal. The output here you're giving as clock signal for this Johnson counter. Here you'll get 2 outputs. Here you'll get 2 more outputs. Okay. Right. So when you're having ring counter, anyway, in the question they have specified, just one second. Here Q3, Q2, Q1, Q0. Q3, Q2, Q1, Q0. Okay. So initial state, they have mentioned Q3, Q2, Q1, Q0 as 0, 1, 0, 1, right? 0, 1, 0, 1. Initial state. Regarding 4-bit counter, 4-bit circuit, they have given initial state as Q3 to Q0 as 0, 1, 0, 1, right? Now for ring counter, the operation is what? Whatever the last stage output is there, that you will get as a serial input, right? So that means when you apply next clock pulse, this 1 will come here, this 0 will come here. When you apply further clock pulse, this 0 will come here, this 1 will come here. That means this particular counter will repeat only two states. Only two states. Yes or no? 0, 1, 1, 0. Only these two states it will repeat. With respect to your external clock pulse, whenever you are getting positive edge, 0 to 1, 0 to 1 transition. This is 2-bit ring counter. Okay. Now, when you're having Johnson counter, here what will happen? Q0 bar you will get as the input, right? Q0 bar. So that means Q0 bar you will get. 1 bar is 0. This 0 you will get. 0 bar is 1. Here, if you want, you can write. This complemented 1 you will get, right? 1 bar is 0. This 0 you will get. Next, 0 bar is 1. This 0 will come. Next, 0 bar is 1. This 1 will come. And once again, do perform. Complement of 1 is 0. This 1 will come. Right? So here, if you observe these four states are going to repeat. Yes or no? Any doubt is there? This is regarding 2-bit ring counter. This is regarding 2-bit Johnson counter based on the initial state. Here initial state is 0, 1. Here also initial state is 0, 1. Here 4 states you will get. Whereas here 2 states you will get. That means this is mod 2 counter. This is mod 2 counter. And this is mod 8 counter. Yes or no? Sorry, mod 4 counter. This is mod 4 counter. This is mod 2 counter and this is mod 4 counter. Right? So that means this ring counter you can replace as mod 2 counter, and the second one you can replace as mod 4 counter. Now tell me what is the overall modulus of this circuit diagram or this block diagram. What will be the overall modulus, mod value? Mod 8, right? Yes, you have to just multiply these two, that's all. Mod 2, 2 into 4, that is nothing but mod 8 counter. Or in other words, if you assume the clock signal frequency is f clock, output of this counter is f clock by 2. Here 2 is nothing but number of states. Okay. So this one is the clock signal for this one, and here you will get f clock by 2 by 4. That is nothing but f clock by 8. So in the denominator, whatever the value is there, that specifies the number of states. That means you can replace the overall counter as mod 8 counter. So if you're having here clock signal frequency f clock, then output frequency will be f clock by 8. Right? So in this way, you can easily figure out what is the mod value for the given circuit. Okay. So here you will get total 8 states. You'll get. Okay. After that, you follow this procedure because he is asked for, after applying 423rd clock pulse, what is the state of the counter? So in the remainder, you are getting 7. So that means after applying 7th clock pulse, whatever the state you are having, the same state you will get after applying 423rd clock pulse. Right? So now you can follow. It is very simple. You have to apply 7 clock pulses, right? Just 1 second. So first, initially I am writing ring counter, that is 0, 1, 0, 1, next 1, 0, 0, 1, 1, 0. This is 2-bit case, 2-bit ring counter. We are getting only these 2 states, right? 0, 1, 1, 0. Now here you are having 4 states. But initial state is 0, 1. Okay. For this particular Johnson counter, the clock signal is what? The clock signal is Q2. Q2 changes from 1 to 0. That time only this particular counter will change from this state to this state. Yes or no? All of you please respond. Here in this particular counter, whenever you are giving positive edge of the clock signal, this particular counter will change from one state to another state. Similarly, this particular count also will change from one state to another state. That will happen whenever Q2 value changes from 1 to 0. That time only. Yes or no? Right? Correct. So here initial state is 0, 1. it will change from 0 1 to 0 0 only whenever q2 changes from 1 to 0, whenever q2 changes from 1 to 0, right? So just observe here in this case q2 is changes from 1 to 0, right? So that means here next state is 0 0, next state is 0 0. So regarding this one, it will continue the same process, 0 1 1 0. Okay, now here 0 1, so there is no change. Here 1 0 change is there, right? So in this case, the next state is what? 1 0. Next state is 1 0. So ring counter, right? Once again 0 0, sorry, 0 1 1 0. So here 0 1 no change. Here 1 to 0 change is there, right? 1 to 0 change is there. So here output is 1 1 1 1 1. Once again repeat 0 1 1 0. So here it will remain same 1 1. Here 1 to 0 happening. So what is the output you will get? After reaching 1 1, next state will be 0 1, right? 0 1 0 1. Just here give the numbering, clock numbering 0 1 2 3 4 5 6 7. If you want, you can continue, then you will get 0 1 1 0, like that you will get. Here in this case 0 1 no change, so you will get 0 1. So that means you can stop here. If you observe here 0 1 0 1 is there, the same state you are getting here. Okay, so that means it is a moderate counter. In this way you can calculate, and here our requirement is after applying 7th clock pulse, what is the state you will be having? The same state you will get after applying 423rd clock pulse, right? 423rd clock pulse. Is it clear, this method? You can follow this method. Okay, you will get the answer very quickly. If you observe the circuit, whatever the circuit is there, you can break the given circuit into n number of parts based upon your convenience. All of you please respond. Is it clear or not? You follow this method in order to get the answer quickly. Clear, right? So whenever you are getting the questions like this regarding counters, okay, so always just observe whether the given circuit is synchronous sequence circuit or asynchronous. Okay, because the flip-flop functionality is based on what? The edge, either positive edge or negative edge. So if you observe the overall circuit is asynchronous because all the flip-flops are not having the same common clock signal. But if you break into two parts, this circuit is having same common clock signal, this circuit is having same common clock signal, right? So individually, this is one synchronous sequence circuit, this is another synchronous sequence circuit, right? So you can analyze this part, and then you can combine like that based upon your requirement. Sometimes they will ask, what is the mod value for the counter of given circuit? Then if you evaluate what is the mod value here, what is mod value here, and then multiply those two mod numbers, that will be your overall modulus of the counter, like that. Whenever they ask like this only, matlab means after applying so and so number clock pulse, what is the state? Then only you have to analyze. Like this. Just 1 second. Yeah. Then only you have to analyze like this up to whichever clock pulse your requirement. In this case, we got remainder 7, so that's why you have to follow up to 7. Suppose if you are getting remainder is 2, you will stop the process here. In this way, it will save the time in your GATE exam. You don't need to do complete analysis. You can do partial analysis based on the remainder value, like that. Okay, right. Yeah, with this we have completed the questions up to sequence circuits. Now we'll discuss the question related to data converters. So for CS students, the syllabus is up to sequence circuits only. Any CS students are there? Yeah. If you want, you can attend this remaining 3 questions which we are going to discuss. Okay, no issue. What are the concepts related to first earlier chapters? If the concepts are involved, you will get some basics. Okay, it's a kind of reason. later you don't need to do any revision or any practice related to these 3 chapters. Okay, for CS branch students. So here the question is related to data converters. An 8-bit analog to digital converter, an 8-bit analog to digital converter with 2's complement output, has a nominal input range of minus 10 volt to plus 10 volts. Input range is this one, minus 10 volt to plus 10 volt. An input of minus 5 volt, will produce a digital output of how much? See, when you're having n-bit case, in the 2's complement representation, what is the range? See here, apparently this question belongs to data converters, but we are using the concept of first chapter only, right? So that's why even if other branch students are there, so please attend the entire session. Okay, what are the concepts related to the earlier chapters? It's a kind of revision for all of you people, right? But later, related to data converters, logic families, microprocessors, CS students no need to practice anything because it is not part of the GATE syllabus, right? In 2's complement form, what is the range? If you're having n bits, minus 2 power n minus 1 to plus of 2 power n minus 1 minus 1. Yes or no? All of you please respond. The range, when you're having n bits in 2's complement form, you can represent negative maximum is this one, positive maximum is this one, right? Negative maximum is this one, positive maximum is this one. Okay, so here he has given one range, minus 10 volt to plus 10 volt. That means minimum value is minus 10, minus 10 volts. Okay, so that minus 10 volt we can represent with this value. So that means minus of 2 power, n value is here 8, 8 minus 1, there is nothing but minus 2 power 7. What is the value you will get? Minus, what is 2 power 7 value? 2 power 7 is how much? $128, right? Yes, very good, Srinivas. 128. Okay, now the question is what? When you're having minus 5 volts, how you can represent? That is the question. See, you're having one range, minus 10 volts. The minimum value you can represent with this minimum value, right? Okay, now the question is at intermediate, some value he has given, that particular value, how we can represent? That is the question. So first, for minus 10 volt, this much. For minus 5 volt, how much? Okay, so you can find like this, right? You can do cross multiplication, minus 5 into minus 128 divided by minus 10. Yes or no? Minus will get cancelled. 5 2s are 10, 2 64s, right? So that means you are getting minus 64. That means minus 5 volt we can represent with minus 64. Minus 64 we have to represent in 2's complement form. Minus 64 is the decimal number. We have to represent minus 64 is the decimal number. We have to represent in 2's complement form. All of you please respond how we can represent minus 64 in 2's complement form. See here the question is related to first chapter only, concept involved, right? Even though this particular question belongs to data converters, but we are using the concept of first chapter, 2's complement method only. Okay. See here you're having minus means sign bit should be 1. Okay, since the sign bit is 1, the corresponding position weight I will consider minus. Okay, you have to choose the positional weight. In powers of 2 in such a way that the least power of 2 that should satisfy, that value should be greater than or equal to 64. Like that you consider. That is 2 power 6. Yes or no? 2 power 6 is nothing but 64, right? 2 power 5, 2 power 4, 2 power 3, 2 power 2, 2 power 1, 2 power 0. So that means here you require 7 bits. You require 7 bits for representing minus 64. Yes, very good, Priya. Yeah, 100 4 zeros. Okay, but here the question is what? You're having 8 bit. You're having 8 bit, but actually we can represent minus 64 with 7 bits only. If you want to represent the same number with 8 bits, what I have to consider the starting bit? All of you please respond. What I have to consider the starting bit? Yes, very good, Priya, Michael. Yes, we have to consider one. We have to consider one because it is represented in two-column format. In two-column form, the starting bit 1. That means what? It is a negative number, right? The same sign bit you can place n number of times to the left of the sign bit. The equivalent value won't change. Okay. So here you can represent with 1. Now, if you do the grouping of 4 bits, you will get the corresponding hexadecimal digits. So 1100 is nothing but C. 4 zeros is nothing but 0. So C0 base 16. C0 base 16. Or in microprocessor, we will use the hexadecimal representation will represent with the letter H. H stands for hexadecimal. In the number systems, we have represented the numbers like this convention, right? We have represented the numbers like this. What the number is there, we'll put within the brackets and we'll put suffix as the base of the number system. In the microprocess, we will represent like this. Here hexadecimal, letter H stands for hexadecimal. We will represent like this. Either this representation or this one, both are same only. C0H. So that means option D is the correct one. Sometimes in the exam, in hurry, some students will do like this. Okay. Here you got 100 4 zeros, right? 4 zeros you will get 0. But here you're having 100, so you will write it as 4. But that is wrong. Because if you're considering 4, here the starting bit is what? 0. That means you are getting positive number, but actually you are supposed to represent negative number, right? So that's why here the starting bit should be 1. Okay, you have to be very careful. Okay. So answer is option D. Answer is option D. Yeah, up to here, the questions related to the data converters for electrical branch. The syllabus is up to here, up to data converters. Now the next question is related to logic family. Especially CMOS logic family. The number of NMOS, PMOS transistor pairs required for implementing the Boolean function f of ABCD equal to sigma m. He has given few terms like this. For implementing this particular function, how many NMOS, PMOS transistor pairs we require? That is the question, right? So whenever we want to get the minimum number, always you have to do the simplification. Right? So here, in order to do simplification, how many variable K-map we have to consider? All of you please respond. Here we are using the concept of K-maps, right? So that's why you please attend the entire session. Okay. What are the concepts involved in the earlier chapters? Those will be helpful for other branches. Okay. How many variable K-map we have to consider? 4 variable. Yes, very good. All of you draw the 4 variable K-map and do the simplification. So in this way, in the GATE exam, sometimes you will get the questions related to the specific chapter directly, or they may combine the concepts of 2 different chapters also. So if you know the basics of each and every concept of each and every chapter, then only you will be in a position to attempt. Otherwise, if you know only partially, you cannot attempt the question, right? Completely. So you have to be very strong on the basics on each and every chapter. Sometimes they may frame the questions of 2 different subjects also. So you have to focus on the basics of each and every subject and chapter. Okay. So wherever in our respective midterm questions, place the ones. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now all of you do the simplification by doing the groupings. And tell me what is the expression you are getting. Here for this particular K-map, there is the possibility of grouping 4 adjacently placed ones. So do all such groupings. Do all such groupings. So regarding this, what is the term? Yes, very good, Michael. So horizontal grouping, row-wise grouping, you will get AB. Here C bar, D bar. Here CD. Just 1 second. C bar, D bar. Here CD. Yes, very good. Yes, Srinivas, Michael. Rashekar, you can cross check. Here you will get AB. CD plus C bar, D bar, that is correct. But here you will get AB. Yeah. So the function is f of ABCD equal to, here in this case all are essential, right? All the groupings are compulsory. So you'll get AB plus C bar D bar plus CD. C bar D bar plus CD. Okay. So this one you can write as AB plus C exclusion or D. C bar D bar plus CD is nothing but C exclusion or D, right? Here the question is what we have to implement this particular function by using CMOS logic. CMOS logic. In the CMOS logic, you will use NMOS transistors between the output and ground. Okay, you will use PMOS transistors between the supply and the output, right? So from wherever you are taking the output, by default you will get the complement version. By default you will get the complement version in CMOS logic. By default, whatever the CMOS circuit you may consider, from where you are taking the output, by default you will get complement version. So here if you observe, you don't have any complement for the entire function. So what you can do, you can apply 2 times complement. The function will be same. You can apply 2 times complement. The overall function will be same, right? Now you can apply De Morgan's law for inner complement. We'll see all the varieties. After that, we can decide. Okay. If you apply De Morgan's law, what you will get? First term complement, and second term complement. We will discuss all the approaches. After that, we'll decide what is the minimum number. Okay. So first term complement and second term complement, and leave external complement as it is. Right. Okay. Now here you're having AB bar. Just 1 second. So just now we have mentioned, from where you are taking the output in CMOS logic, by default you will get complement version, right? So under the complement you're having what? 2 variables. Under the complement you're having 2 variables, A and B. That means you require 2 NMOS transistors in series. 2 NMOS transistors. See here, very simple. Whenever you're having logical AND, that means we will connect NMOS transistors in series. NMOS in series will connect. Okay. Exactly opposite will connect PMOS. That means 2 PMOS transistors will connect in parallel like that. For logical OR operation, if you're having under the complement, I am talking. Under the complement, if you're having logical OR, will connect NMOS transistors in parallel. Is it clear? Any doubt is there regarding these 2 conventions? For NMOS it is series. Obviously for PMOS it will be parallel. NMOS here parallel, for PMOS it will be series. Whether do you know this concept or not? EC students and IN students can respond. Regarding CMOS logic, whatever I am saying is, under the complement, if you are having logical AND among the variables, will connect NMOS transistors in series. Here in this case, you are having 2 variables. So I will connect 2 NMOS transistors in series and 2 PMOS I will connect in parallel. Here if you are having A plus B, then we will connect 2 NMOS transistors in parallel like that. Right? So this concept you are very much familiar, right? Okay. So for implementing AB bar, See here the question is what? You have to find the number of NMOS PMOS transistor pairs. If you can calculate the number of NMOS transistors required, the same number you require for PMOS, right? So just focus only NMOS. So here under the complement you're having two variables among which logical AND operation is there, right? So you require two NMOS transistors. Two NMOS transistors. Okay, just focus only NMOS. The same number you will get for PMOS also. Okay, fine. Next one is what? C exclusive NOR D whole bar. C exclusive NOR D whole bar. This one you can write as C bar D bar plus CD. C bar D bar plus CD whole bar. C bar D bar plus CD whole bar. Okay. So for the timing, I will write this one like this. This is like x1 plus x2 whole bar. It's like x1 plus x2 whole bar, right? So where x1 equal to C bar D bar and x2 equal to CD. X2 equal to CD. Okay. Or directly also you can write. No issue. So here if you observe, here you're having CD. CD means what? Series connection. CD means series connection, right? So that means how many NMOS you require? How many NMOS you require? Here you are having overall complement you are having. After that you are having two terms. This one term, this another term. Here among the two variables logical AND is there, right? So that means you require two NMOS. You require two NMOS. Yes, very good. Here you are having C bar D bar. See, whenever they don't specify in the question regarding complement inputs, you have to implement. You have to implement the complemented version, right? So for implementing C bar, you require, just observe under the complement, you're having only one variable. So that means you require one NMOS. Similarly for D bar, you require one more NMOS. Okay. After that, assume C bar is something like X1, D bar is something like X2. Now just observe here. For implementing X1, X2, you require for X1, X2. That is C bar, D bar. How many you require? Just like here, CD means two variables. Here also two variables. So that means you require two NMOS. Is it clear? See, from where you are taking the circuit output, by default you will get the complement version. That is the CMOS logic. Okay, fine. Under the complement, just observe the terms. Here you are having two terms. Those two are product terms. Right? So first observe. Here you are having two normal variables. So that means you require two NMOS. Here you are having two complement variables. So for each complement variable, you require one NMOS. After that, consider these two complement version as normal variables like X1, X2. So for X1, X2, you require two NMOS. Okay. So that means, so after that, it is very simple. Just you can visualize like this. What I'm saying here is, here regarding CD, I will connect two NMOS in series. Okay. Just in order to get easy understanding. Okay. I will give C and D are the inputs. This is series connection. Okay. Here C bar D bar, logical AND is there. So here I will use two NMOS transistors in series. But the inputs are C bar D bar. So C bar you can generate with the help of one CMOS inverter, D bar with the help of one more CMOS inverter. Okay. So here you will get CD, here C bar D bar, right? So here if you observe under the complement, you're having what? This is like Y1, this is like Y2. Y1 plus Y2 you're having, right? Plus means, here plus means what? Logical OR. Logical OR means what? Parallel connection, right? So this NMOS section, we will connect in parallel. Is it clear? All of you please respond. Are you able to correlate how the circuit diagram look like? Actually, I have drawn only part of the circuit regarding NMOS. Okay. Other part will be there regarding PMOS. Yeah. So here for implementing C exclusion or D complement, you require total 6 NMOS transistors. You require 6 NMOS transistors. For implementing this particular expression, you require 6 NMOS. Okay, right. Now, after this, consider this like x1 into x2 whole bar. X1 into x2 whole bar, where x1 is this term and x2 is this term. Okay. See, you're having complement version. Okay. Under the complement, you're having two terms. First term is x1, second term is x2. Okay. So AV bar you will generate with the help of CMOS logic. That output you will get somewhere, and similarly you're getting output of this particular expression somewhere. Okay. After this, next step is what? Here you're having logical AND, right? So that means you have to use two NMOS transistors. Yes or no? You have to use two NMOS transistors in series. All of you please respond. Where x1 is AV bar, x2 is this expression. Okay, so that means just add all these 2 plus 6 plus 2. That means 4 plus 6, 10 NMOS transistors we require. Similarly, 10 PMOS also you require. 10 NMOS transistors, 10 PMOS. So that means we require 10 NMOS PMOS transistor space we require. 10 NMOS PMOS transistor space we require. Okay. So with the help of this logic, we got like this 10 NMOS PMOS transistor space. Now, what are the expression is there? Right, once again, what are the expression you got? Right, once again, that is AB plus C exclusion or D. AB plus C exclusion or D you're having, right? So since you are getting complement version in CMOS logic, for that sake, I have applied 2 times complement. Okay. So previously we have applied De Morgan's law for inner complement and we have proceeded. Now, instead of like that, so what we can do, I am representing this one as something like this, y1 bar. So what are the expression is there? This entire expression I have labeled as y1. Okay. So first let us analyze for y1. Y1 is nothing but AB plus C exclusion or D whole bar. AB plus C exclusion or D whole bar. Okay. Now, for y1 bar, if you observe here, y1 bar is there, right? So you require one NMOS because under the complement you're having only one variable, so you require one NMOS. Fine. Now, just observe here you're having complement version. Okay. Under the complement you're having two terms. So here it is the logical AND. So that means how many NMOS we require? Two NMOS, right? Yes. We require two NMOS. Very good, Michael, Srinivas, Rajshekhar. Yeah. Priya. Yes, very good. We require two NMOS. Now, one more expression is what? C exclusion or D. All of you please respond. For implementing C exclusion or D in CMOS logic, how many NMOS transistors we require? We have discussed that concept in the class, right? So how many NMOS transistors we require? Minimum number for implementing C exclusion or D. Not 4. It will be 6. See, C exclusion or D you can write as complement of XOR, right? So this one you can write as C bar D plus CD bar. Whole bar. Now just observe, you're having complement version. Under the complement, you're having two product terms. Just observe here, under the complement, you're having one product term. Variables are AB. When you're having variables normal form, you require how many variables you're having, that many NMOS you require. But here, if you observe, you're having two product terms. Here, you're having one complement term, that is C bar. Here, another complement term, that is D bar, right? If you're having both are normal variables, then you require two NMOS. Here also two NMOS, but one variable is complement. So how many NMOS we require here? How many NMOS we require here? All of you please respond. 3, right? 3. Very simple. Very simple. What are the product terms you are considering? In all those product terms, just observe whether any particular complemented term you are having. If any complement term is there, if it is repeating, you can implement for one time. If it is not repeating, you have to count. Okay, you have to count in each and every product term. If you're having the variables normal form, how many variables you're having, that many NMOS required. But if you're having complement version, how many complement version you're having? So you have to consider extra one. That's all. Here normal variables are 2 because you're having complement, so you have to add 1. That's all. 2 plus 1. 2 plus 1. Similarly here 2 plus 1. Okay, like that. So that means for implementing XNOR gate or XOR gate, we require 6 NMOS transistors. Similarly 6 PMOS transistors, right? So here we require 6 NMOS. 6 NMOS. Okay, right. So here we require 2 NMOS. Here we require 6 NMOS. So you're having one circuit diagram from there. Okay. So here it is something like this. Just for easy understanding, I will draw the circuit diagram here. Part of the circuit diagram I am drawing. So here you will be having 2 NMOS transistors in series AB. Okay. So here you will be having C XNOR D. Okay. I am just representing C XNOR D NMOS logic. NMOS logic. Okay. For the timing, I'm not drawing. Whatever the expression here you're having, I'm not drawing. Okay. But here you'll be having NMOS logic. NMOS transistor logic you'll be having regarding C XNOR D. So this is one path, this is another path. Okay. Here you're having what? Plus. Plus means parallel connection. Plus means parallel connection. Is it clear, everyone? Up to this step. Regarding C exclusion or D implementation, what are the NMOS logic is there? That for the timing I have represented with one block. Okay. Here you're having NMOS logic. Here NMOS logic. Since you're having plus symbol, you have to connect them in parallel. Okay. So from here you will take the output. By default, you will get the complement version. And similarly, you will be having PMOS logic on top. Here, if it is series connection, they are parallel connection. If it is parallel, they are series. Up to this step. All of you please respond. Regarding Y1 expression, we require 8 NMOS transistors. Similarly, 8 PMOS we require, right? Yes. Now just observe. The overall function is what? The overall function is Y1 bar. Y1 bar. So for Y1 bar, you require 1 NMOS. For Y1, you require 8 NMOS. 8 NMOS. So if you add these two, you will get 9, right? You will get 9. 9 NMOS PMOS transistor pairs we require. 9 NMOS PMOS transistor pairs we require. So previously what we have done, I have applied De Morgan's law for inner complement because, okay, so in that approach, I got here 10 NMOS PMOS transistor pairs. But here I haven't applied De Morgan's law. First, I have implemented this particular function. After that, I have complemented. So in this case, we are getting 9. So whatever the least value is there, that one will be the answer because the question is what? The number of NMOS PMOS transistor pairs required. Okay, so that means always they will ask for minimum number only. If you want more clearly, you can mention here the minimum number. Otherwise, always you have to specify the answer as minimum number only. Okay, regarding minimum number, answer is 9. I hope it is clear for everyone. So regarding CMOS logic, either they will give like this expression and they will ask regarding any logic gate or any logic function, what is the minimum number of NMOS PMOS transistor pairs required, or they will give one circuit diagram and they will ask what is the output expression, either sigma m format or pi capital M or simplified version, etc. Right? Only these two variety of questions you will get from this particular concept. Okay, so for EC branch, the syllabus is up to this particular chapter, right? Up to logic family only. Now this is the last question regarding microprocessor. Consider the following program of 8085 microprocessor. Here he has given the program like this, and he is asking after execution of above program, the contents of accumulator will be dash, represent in decimal format. Okay. So here he has given instructions. We'll do step by step. Here L stands for load, I stands for immediate. Whenever the symbol X is there, okay, that specifies what? It is a register pair. Here in 8085 microprocessor will represent with one letter only, but here if you observe, you're having 16 bits, or you can say 4 hexadecimal is both are same, right? So that means it is not 8-bit register, it is a 16-bit register, right? So what are the data here you're having that will go to BC register 2006. See, in 8085 microprocessor, we are having like this BC, DE, HL. Whenever 16-bit requirement is there, they will use the pairwise 8-bit registers like this BC, DE, HL. But in the instruction, they will specify always the higher order register name B or D or H like that. Okay. Next, XRA. That means A exclusive or with A only. By default, all arithmetic and logical OR operations. For all arithmetic and logical operations, by default, one of the operand is accumulator, and another operand they will specify here in the instruction, and the result will be stored back into accumulator. Here in this case, we are performing exclusive OR operation among the same value. What is the resultant value you'll get? All of you please respond. When you perform XOR operation on the same value, what you will get? Resultant value. You are very much familiar, right? Just like X exclusive or X, you will get 0, right? If both are same, output is 0. Here you have to represent with 8-bit case, so that means 00 hexadecimal. Here each and every digit you can represent with 4 bits. Okay. Yeah. Yes, Shubham. Yeah. 00H. Now, here LD means load. HL means HL register pair. Okay. Here you're having one memory location 2001. But here you're having 16-bit register. In each and every memory location, you can store 8-bit data only. But here you're having HL. H register capacity is 8-bit, L register capacity is 8-bit, right? So that means here we have to consider from two locations. One location is 2001. Another location is 2002. Just 1 second. One location is 2001, another location is 2002. Now just all of you please observe, among these two locations, which is the higher order one? First one or second one? Here you're having two locations. First one is 2001, second one is 2002. Among these two, which one is the higher one? Second one is the higher one, right? Second one is the higher order, right? So always in this entire microprocessor, only one logic. Always higher order memory location points to higher order register. Lower order memory location points to lower order register, right? Here you're having HL. H is the higher order register, L is the lower order 8-bit. H is the higher order 8-bit, L is the lower order 8-bit. Okay. So always higher order memory location points to higher order register. Lower order memory location points to lower order register. So in this memory location, whatever the 8-bit data you're having, that will come here in this particular register. Similarly, in this particular memory location, what is the content you're having 8-bit data, it will come here. Now, where you're having the contents of 2001, 2002, whether anywhere he has specified in the question, the contents of this location and this location. Directly not specified, but if you observe, the data is available. Just observe here. Here, for each and every instruction, the starting address is there. So in the starting address, for each and every instruction, you're having mnemonic, right? So regarding this particular instruction, you will be having opcode, 8-bit code. You will be having that particular data will be present in this particular location for each and every starting address of the instruction, right? Okay. After that, here if you observe 2 bytes, you are having 2 bytes. Okay. So here 2000. After that, next location is what? 2001, 2001. So in that location, you will be having 06, 06. Next location is what? 2002. In that location, you will be having 20, 20. Okay. After that, that's why here next instruction is 2003. Next, here you don't have any data. That's why next one is 2004, like that. Okay. Is it clear? Any doubt is there? Yes, Prajapati. Entire syllabus will be covered. Yeah. Now, next one is what? Move immediate a comma 40. That means accumulator value is 40. Accumulator value is 40. Now, next instruction is compare M. Compare M. So that means accumulator contents will be compared with accumulator contents will be compared with memory location. Here, memory location is what? Contents of HL. Contents of HL. So that means here accumulator value is 40, 40. HL, H value is 20, L value is 06. H value is 20, L value is 06, right? 2006H. So now tell me, in this particular memory location, what is the content you are having? All of you please respond. In this particular memory location, what is the content you are having? 2006. See here, 04 location, this opcode you are having, 05 this location, 05 location you are having this content, 06 location you are having 20. You are having 20. See, this is a very, very important instruction in the microprocessor. The microprocessor will perform subtraction operation. The microprocessor will perform subtraction operation just in order to update 2 flags. One is carry flag, another one is 0 flag. Okay. In order to update these 2 flags, the microprocessor will perform subtraction operation whenever you are getting compare instruction. But the microprocessor won't store. The result won't be stored in the accumulator. After performing subtraction operation, what are the result you are getting? That won't be stored in the accumulator. Just in order to update these 2 flags, your microprocessor will perform subtraction operation. Now tell me, after performing subtraction of these 2, whether do you require borrow? Here carry is nothing but borrow only. The same flag we can utilize. Okay. Whether do you require borrow? No, right? 0. After performing subtraction operation, since these 2 are not same, 0 flag will be 0. If these 2 are same, then all the bits will be 0. So that means 0 flag will be set. 0 flag will be set. Right? Okay. Next. So that means here, after performing this particular instruction, 0 flag is 0. That means whether this condition is true or false. Jump if 0. Whether this condition is true or false. See, this condition is true if 0 flag is set. But here 0 flag is reset. That means this condition is false. This condition is false, right? So it won't jump to 2014. It won't jump. Okay, it will execute next instruction. Here RAL. RAL is what? Rotate accumulator left through carry. Rotate accumulator left through carry. So that means here you're having accumulator value is 40. When you're performing rotate accumulator left through carry, here you're having 40, right? So that means it will be multiplied by 2. Multiplied by 2. So that means you'll get 80H. 80H. So carry value will be 0. Because here 4 is nothing but 0100. The starting bit is 0. That will go to the carry bit. That will go to the carry bit. Whatever earlier carry you're having, that will come to the your LSB of the accumulator. Since you're having carry value 0, here 40 is there, you have to multiply with 2. It is very simple. Otherwise, you can perform rotate accumulator left through carry. Through that process also, you'll get the same answer for this particular example. Okay, right. Next, load immediate H comma 2008. So that means HL equal to 2008. Okay. Now, exclusive OR operation among these 2 you have to perform. A exclusive OR contents of HL. A exclusive OR contents of HL. Okay. So accumulator value is 80. Just now we got 80H. Exclusive OR with HL. HL value is what? 2008. Now tell me, in this particular memory location, what is the content you're having? All of you please respond. In this memory location, what is the content you're having? 2008. Just observe 2007 here is there, 09 here is present. That means this will be 08 location, right? 08 location. That means 40H. So if you perform exclusive OR operation, you will get C0H. You convert both the numbers into binary. Okay, after that perform exclusive OR operation. From there you will get 0 XOR 0 is 0. Okay, 8 is nothing but 1. 8 is nothing but 10000. 4 is nothing but 0100. If you perform exclusive OR operation, you will get 1100. That is nothing but C0H. Right. So this is your accumulator content. This is your accumulator content. Now, next instruction is complement accumulator. That means accumulator contents you have to complement and the result you have to store back into accumulator. Result you have to store back into accumulator, right? So here you're having C0. That means 1100 4 zeros. If you make complement, once complement, you will get 0011 4 ones. 0011 4 ones. That is nothing but what? 3F. 3F hexadecimal. 3F hexadecimal. Okay. After that, next step is halt. Halt means microprocessor will stop the process. Okay. Here the question is what? The contents of accumulator in decimal format he is asking. Here you got hexadecimal number. All of you please convert this hexadecimal number into decimal. Hexadecimal number into decimal. What is the number you will get? All of you try to solve. This is the concept based on the first chapter, right? All of you please respond. What is the equivalent value you will get? See, 16 3s are 48 plus 15. So that means you will get 63. So the decimal equivalent is 63. 63. So in this way, from the microprocessor, you will get either the programming, either they will give us some set of instructions, they will ask what is the contents of some accumulator or some register, or where the result has been stored, or in some memory location, what is the content available, or what is the status of flags, etc. Or you may get the theoretical questions also, or maybe interfacing, memory interfacing, address range, etc., valid address or invalid address, etc. And regarding 8086 microprocessor and 8051 microcontroller and programmable logic controller, distributed control system, just focus on the basics. Okay, you will get the theoretical questions or very basic questions you will get from those concepts. Okay. I hope just one thing. I hope this session is benefited you. Please like and share this video with all of your friends so that they also can watch this particular session since it is available in YouTube, right? Later. Even you also can watch this particular session later if you want to refer. And please subscribe the GATE Academy channel. Thank you all.